In this lesson, we're going to focus on both Objective 5.7, Introduction to Reaction Mechanisms, and 5.8, Reaction Mechanism and the Rate Law. It's kind of great to put both of these together just because they kind of work hand in hand, and what I have to mention in 5.7 will just quickly flow to 5.8, so it's easier to put them both together. So 5.7's learning objective is to identify the components of a reaction mechanism. Okay, and then 5.8 is you can actually figure out a rate law for a reaction from the mechanism, and it's through something called the rate determining step, also known as rate limiting, which we'll talk about in this objective. So recap from 5.4. I wrote 5.3, it's 5.4. Recap from 5.4, we did briefly talk about reaction mechanism, and it consists of a series of elementary reactions or steps that occur in sequence. And we saw in that learning objective, we saw, one step, two step, and the overall would give us the balanced equation if we took the sum of those elementary steps. And we looked at reactants, intermediates, products, and catalysts. So here we're going to dive in more about these reaction mechanisms because it's a very, very important concept in kinetics. So when it comes to reaction mechanism, it has to meet two things. The first is, which we focused on in 5.4, it must add up to the overall balanced equation. Again, we talked about this in Objective 5.4. The next one, which is going to be the focus of this double unit, it must agree with the experimental rate law. So this is this current Objective 5.8. Okay. So, when I say experimental rate law, here you sometimes would be told a rate law, or it also could be that the mechanism just comes from the rate determining step, which we'll talk about here too. So it can be either of them just based off how the question is structured. So we can't prove a mechanism absolutely, because think about it this way. We will not really actually see the intermediates working in action when the reaction occurs because we're not at that particle level. So we can come up with a possible mechanism and look through different data to give us insight like, oh, did that catalyst work how it was supposed to? Did that intermediate help make the reaction occur? So we can kind of figure it out, but we can't really prove it exactly. So sometimes it comes down to theory, okay? So reaction mechanisms and the rate law. So the speed of a reaction is limited by the speed of the slowest step. So here, this will be the greatest activation energy. Okay, this will come into here shortly in the next couple of objectives. This slow step we call the rate determining step. Because if you think about it this way, if your slow step is going to be the longest for that reaction to occur, that's going to affect the entire rate law, with that rate law being, 0 first and second for those reactants. So in this case, it will determine the rate law of the overall reaction. So we're going to actually end up using stoichiometry of those molecules, so the stoichiometric coefficients that will tell us whatever that coefficient, it will be what order it is with respect to that reactant. So let's look at this reaction right here. All right. So we have 2 hydrogen, 2 NO making nitrogen and 2 waters. Okay. So it was experimentally determined that the rate law is this. Okay. So again, they probably took some data from doing different trials, saw that hydrogen was actually first order and NO was second order. So the fact that you notice right away that this doesn't actually match up from stoichiometric coefficient to the rate law as mentioned previously about the rate determining step, this tells us that this isn't a single step reaction. So it basically confirms the fact that this has to be a type of mechanism. So the fact that the overall does not match rate law experimentally determined, this signifies this is a reaction with a series of steps. So this has to be a type of mechanism with multiple elementary reactions. And if you see below, the student actually proposes that the reaction mechanism for this reaction is based off 3 elementary steps. So let's look at this. This is different than 5.4 because we never gave you this type of information: slow, fast, and fast. Okay, so now starting off now, you should be given those pieces of information. So remember, based off a reaction mechanism occurring, we have to make sure that the balanced overall equation is occurred from the sum of all 3 elementary steps. And then the second one, for the reaction mechanism to occur, we have to see if the rate determining step gives us the rate law. So I'm going to zoom in here and I'm going to start with the first one. Okay. So here, let's see if we have any intermediates or intermediates or catalysts. So here I notice the nitrogen is a product and the reactant in the second. So this tells me that this is an intermediate. So I'm going to cross that off. You also will notice we have oxygen, okay? So the oxygen is a product, also a reactant. So I'm going to cross that off. I don't see anything else. So let's see if this matches my balance overall from the start. So 2 hydrogen plus, 2 nitrogen monoxide, making 1 nitrogen and 2 water. So right now, this does match up with my balance. So mechanism added up to balanced overall, equation. So here, this worked and matched to the overall. So far, the first one is good, but we have to make sure the second one also works. So based off what we learned in this unit, the slow step, which is generally the first step, will tell us the rate law based off the stoichiometric coefficients as the powers for those reactants. So looking at the slow step, our rate law is K, hydrogen raised to the first power because of its stoichiometric coefficient, and then nitrogen monoxide raised to the coefficient of 1. So here, slow step gives us that the rate law is KH2NO. Now the issue is, we were told that through experimentally determined data that the rate law is this, showing hydrogen is to a first order and that the nitrogen monoxide was raised to the second. So here, this does not correlate with experimentally determined rate law. So here, this would not be an acceptable mechanism because we had to make sure that the first and the second were satisfied. So here, this student didn't propose an accurate reaction mechanism, okay? All right, I have this example for you right here. Consider the reaction below, and it was observed that its rate law is K, taking NO2 raised to the second power. Now, it just happens that the overall ended up correlating with coefficients, but that doesn't always mean that it's going to be the case every single time. This does represent that it is a mechanism, just because we have these example problems of mechanism 1, 2, and 3. So what you're going to do is you're going to ensure that both two qualifications occur. That if you take the sum of all three steps, it matches to the balanced overall. And then you're going to look at the slow step and see if that correlates to the experimentally determined rate law, okay, which is this K, rate equals K NO2 squared. So pause the video, see if any of these mechanisms work, see if there's more than one, see if none of them work. So yeah, pause the video and try this out yourself. All right, so looking at this example that you just did, okay, here, what was nice about all three mechanisms, they did, after taking the sum of every single step, I did get the overall balanced equation to match to the original. So that's good. The issue is when I took the slow step, the rate determining step, it did only one matched up to the experimentally determined one, which was mechanism 1. Mechanism 2 and mechanism 3 showed that NO2 was a first order reaction when it was just showed, which was already proved that NO2 was second order. So mechanism 2 and mechanism 3 did not make the cut as the correct mechanism. So only mechanism 1 would be the correct mechanism for this reaction because it was consistent with the overall balance and the rate coming from the slow step, which was the rate determining step.